Cool. Should I start?
Yeah, sure.
Awesome. So I've kind of prepared a few slides. The topic, right, was how do we leverage machine learning in an organization like Corteva. I'm going to be talking to you a little bit about different areas or different groups, mainly along the breeding side of the organization and how we can leverage different types of modeling in the end to create a better product, right, that we can sell to farmers. Um, and so I'll talk a little bit about, introducing genetic variation within a population, how we can model how that genetic variation interacts with the environment and predict how it will perform, and then just some approaches that we've taken as a company to do that. And then some background. So I'm the precision phenotyping validation lead. So my group mainly works on developing precision phenotyping technologies. So I'll focus then kind of the remainder of the time on what my group does and some of the things we've been working on in the precision phenotyping space. Um, you've probably all seen, I don't know, well, if you've taken any breeding courses or listened to anyone in industry from the breeding side talk about, breeding, they always show breeding as a funnel, right? And really the concept is we want to be able to widen the funnel as much as possible in terms of, how can we, so there's so much genetic variation available, right? And really the combinations we can do are almost endless, especially nowadays with some of the new technologies. We can introgress any number of genes that are available. We can make any number of crosses. We're working with plants, right? So it's really easy to cross them and create recombination. We can you know uh, create mutations. We can do all sorts of things, right? And so introducing genetic variation to a population is really easy, but what's not as easy is going out and actually testing that novel genetic variation. And so we've been relying a lot, especially after marker assisted selection, on making predictions of, okay, what happens if I introduce this gene, if I upregulate this gene, or if I make this cross and get recombination, what's going to happen to my population? And so we rely a lot on predictions and running models to simulate what happens when we introduce genetic variation so that we can then decide, okay, this is what we actually want to do, and this is what we want to test, right? So we'll simulate all of this genetic diversity and then decide, okay, let's actually go out and test a subset of that. So we want to widen the funnel as much as possible, but we want to immediately shrink it back up because testing in the field requires a lot of resources. It requires a lot of time, a lot of effort. You need to collect data on what you're testing, etc. And then we also want to shorten the funnel as much as possible because we want to get products out fast. So we don't want to spend many years evaluating the same products so that we are confident that that product is stable across, many different environments. We want to make this as quick as possible so that we can release products out fast that are going to help our farmers. And so, there's different ways we can do that. But a lot of it is leveraging different models to predict things like G by E in order to get a better assessment of the different genetic elements that we're testing, and then make more informed decisions along the way. And also another component that's maybe not as straightforward or not that people don't think about as much is, where do we actually test these varieties, right? We have so many options, so many regions, right? We create products for farmers all over the world. So how do we actually select specific environments or specific testing locations and optimize, right, those selections in order to, get a good assessment of where our products are gonna perform the best in say in this grower field, this product is gonna have better performance. So we rely basically on modeling for a lot of these components from making predictions of what we want to actually test in the field and then selecting what fields we actually want to test on and then what germplasm we want to advance and eventually commercialize. And all the phenotypes that we care about, most important one for the most part being yield, but there's many other ones, right? Like disease resistance, heat resistance, drought resistance, flooding resistance, wind resistance, etc., they are relying on the interaction of the genotype with the environment, and then again this G by E component that's sometimes really hard to measure. And then this, you always have kind of this residual error that you can't really empirically measure, that's going to have an impact on the phenotype. And so how do we reduce that error, improve our G by E estimation, in order to get better predictions of our phenotypes? I kind of talked about this a little bit, but just briefly, right, we can introduce genetic variation in many different ways. Some of the key ones are transgene, genome edits, mutations, introducing native exotic alleles. And, when we think of a lot of these genetic elements, we often think about them in kind of this binary classification. Does it have an impact? Does it not have an impact? But that's really rarely ever the case. So for example, if I upregulate this gene or introduce this, do this gene edit, and it's gonna cause my plants to be short because it has an impact on growth hormone pathway. And so people might say, okay, well, is it short or is it tall? But again, that's rarely ever the case. What we often see is that there's unintended consequences to almost every genetic variation that we introduce. And so you might be impacting other traits, say, I don't know, root structure or root depth, etc. And so understanding those impacts is really important, based on the genetic background. But then also, normally that effect is not very straightforward. You can often get some sort of quantitative effect, right? So it's not always, is it short or is it tall? Sometimes you can get, if I introgress this gene into a whole population, I'll get overall that the mean of population with the gene versus without, is taller or shorter. But it's not as clear cut if you're just evaluating like a small pool of germplasm with limited backgrounds, right? And so, along those lines, making sure that you're evaluating genetic variation on a population basis becomes really important. And more so, you can also get, of course, genotype by environment interactions. So maybe the phenotype is expressed in some environments, in some genetic backgrounds, but not in others. I think I got a beep. Let me open up my chat here. I don't know if someone put something in the chat. Okay, I don't know how to go back to the chat window. Let me know if someone writes a question, and then I can address it. Not sure where my chat window went. Okay, so yeah, I kind of talked about this a little bit, but there's many challenges with working with transgenes or any of these methods to introduce genetic variation. You can get unintended effects like penetrance, pleiotropy, epistasis, etc. So these genetic elements are interacting and maybe causing other genes and having other effects on other phenotypes as well. And then you also almost always get some sort of transgene by environment interaction. So the effect will vary by environment, and they'll also vary by genetic background. And so again, making sure that you have a good understanding of genetic backgrounds and their impact across different backgrounds can become really important. But what happens is we have molecular data for a lot of different genotypes. And so in early testing stages, we can simulate all of this genetic variation. We can generate predictions on millions of lines, but we have very little testing data on those, right? We haven't really empirically tested any of it. We don't know if it's true. It's as good as our models are, right? And so these predictions can sometimes not be very accurate. So then it is important to then take these lines that we predict are going to be superior and then actually test them in the field. And so in beginning stages, we'll test them on very few locations, but then towards the end, then what we end up with is very few lines that have kind of made it across multiple years of testing. And we're testing these few lines across many, many different locations in order to get a good estimate of, yield stability across environments, and get a better understanding of that G by E pattern and making sure that those lines are actually stable. And so, yeah, so again, this plays into understanding that G by E interaction, right? So in the beginning, we have very little information on G by E patterns. We mainly rely on genetic information to make decisions. But then as we test in more and more locations, we move more towards empirically driven data to make our decisions. And so, then the question becomes, okay, so how do you go about understanding some of these G by E effects and actually modeling them, right? And so I'll show you two examples of things that we've done in Corteva. So this is an example from Frank Techno. It's published, it's in a paper. And so one approach that you might take is, okay, so for example, if I introduce this transgene or, if I make this cross, et cetera, I'm predicting that I'm going to have this specific effect in terms of a specific trait. So say I'm going to increase my leaf area index, I'm going to increase biomass, I'm going to increase radiation use efficiency, et cetera, via a specific pathway. You can start to understand some of these mechanisms, but that doesn't necessarily mean that you're going to have the intended impact across environments that you haven't really tested, right? And so what Frank did was, okay, what if we combine crop growth models and the information we can obtain from them with whole genome prediction? Because whole genome prediction, again, you're just predicting based on molecular data. So there's very little information on the G by E pattern. And so what he found is, I don't know if any of you remember 2012. I remember that it was my first year. My first time moving to Iowa to go to college at Iowa State, and it was a huge drought year. And I remember everyone was kind of freaking out because of yields, right? Major drought. There was going to be, very low yields, et cetera. So it was a year that was very outside the norm because, a huge drought. And so what happens, right, is, okay, and that happens for different aspects in different regions. Maybe it's a abnormally cold year, maybe you had to plant really late or harvest really late, et cetera, right? There's always elements of the weather that might not fit the norm that could happen, and especially now, right, with global warming and all of these changes that are happening in the environment, we're getting more and more outside of the norm or what you would expect. And so if we were to just rely on data, for example, from 2012 or data just from 2013 to predict a different year, right, a different environment that the model hasn't seen, if we just use marker data, we would get very low prediction accuracy when trying to predict across years, right? So that's these two middle lines over here. But then once we combine it with crop growth modeling, we can greatly improve the prediction accuracy because we can better model those G by E patterns. So again, this is some work that's published, so feel free to look up the paper, and this is by Frank Techno. And so you can apply this, right, when you're thinking, okay, how do I expand this, not necessarily to just across years, but to different regions, different environments that you really haven't tested before. But it does require, right, investing in a training set to kind of start building your models. And so, another component is, okay, for understanding G by E patterns and knowing, making predictions in new environments, you need to model the environment in some way, right? You need to understand what are the parameters that are impacting the specific trait in a specific environment or location. And currently this has gotten a lot easier. It's still challenging to some degree, but there's a lot of data that's available that allow you to model the environment. There's tons of weather data available that we can pull. There's physical features, soil maps, terrain maps, et cetera, that are available. In companies like Corteva, we invest quite a bit in developing some of these resources as well within our testing footprint. So making sure we're getting, soil samples, not just in our research fields, but in farmers' fields, so that we make sure we're aligning our testing footprint to the customers. Management features are still a little bit of a challenge. We do internally collect some management practices, but it's still kind of challenging, especially when we're trying to understand management practices from some of our farmers or cooperators. Oftentimes this is not data that's really available anywhere. So things like whether what their fertility regimen is, irrigation, etc., can be a little bit challenging still, but I think we're getting a little bit better, at least in the research side internally, at documenting some of these practices. And then, of course, this is probably what's being most utilized nowadays, aside from weather data, is actually collecting in-season phenotypes with remote sensing. So, for example, satellite data can give us really good insight into how crops are progressing throughout the season, which can give you some indication, for example, on when a field was planted, maybe a little bit of insight into management, some insight into growth, and response to some of the weather parameters. And more importantly, it allows you to get data throughout the season and then help you cluster environments when combining the remote sensing data or phenotyping data with some of the other parameters, and then understand, okay, these environments are very similar, so I would expect, right, that then these specific hybrids would respond in a similar manner to these environments. So about regards to environmental clustering. And then there's 3 examples in literature that I've listed out here that help or give you some examples of how to do this at scale, right? So doing large scale environmental characterization using some of these features. I'm gonna talk about one of them, which is modeling planting date. This was a collaboration between Corteva and Stanford. Basically, they compiled Landsat satellite imagery from 2000 to 2020 across over 28,000 maize and soy fields across 12 states in the US. And they use this to basically then try to understand trends in planting date by region. And really, in the end, what they're doing is developing these models and get a better understanding of, okay, how do my weather and soil parameters affect planting dates, and how can I use this to help best place different varieties and optimize my selection strategy of specific varieties. And the name is over here if you want to read more about this. And satellite data satellites is one piece of technology that has been drastically evolving through time. So only a couple of years ago, I remember like it was really hard to get sub-meter data from satellites available, even if you had to pay for it. Now we can easily get 30 centimeter satellite data for our fields, and we've so constellations like SkySat can give you that. And more recently, right, there's newer constellations that can get all the way down to 10 centimeter resolutions like albedo, which is I think currently the legal limit. I don't think we can go below 10, but you can imagine each pixel is 10 centimeters big, and so that's actually a really small part of a really small area, and so it does allow you to get down to plot level phenotypes in theory. And so satellites are progressing so much that they can give you a lot more information and elucidate a lot more spatial trends in fields, but also allow you to obtain different phenotypic data that previously you would have to either go out to the field or measure with other technologies like drones. And so this is another work done by Eli Rogers-Melnick. He's another coworker here in Corteva, but he's basically leveraging that similar idea. But okay, so let's take all of these available satellite imagery that we have historically. We have so much phenotyping data as a company, right, for a lot of our germplasm. We have all of the molecular data for that germplasm as well. We have a lot of remote sensing data, from drones, different phenotyping platforms, and then we have a lot of ground data as well. We have yield data for all of these as well. So let's combine all of that data into a machine, a deep neural net, and actually elucidate trends that we can then use within a latent representation to be able to identify, okay, this is how specific hybrids perform in specific clusters of environments, and then leverage that information to then predict, okay, so this is how specific combinations of genes might work best in this combination of environments. And if you're not familiar with latent representation, it's just basically, extracting features that represent kind of the spatial trends that you're seeing within a data, or the structure of your data, right? And so like a classic example is something like a PCA, but there's some, there's some newer ways of getting latent representation. So things like GANs, for example, are commonly used now. So it allows you to combine data from different sources, because in the end, you're just getting kind of this abstract representation of the general trends that you're seeing in the data. And so in the end, what we have, right, are these predictions, right? This is how these genetic elements are gonna perform in these environments. And you have this kind of distribution, right, of predictions. And so you're selecting the top contenders. These are my top contenders. This is what I wanna produce, and then actually characterize in the field. Then often, when you actually characterize them, some of them do not hold up to their predictions, so then you're feeding that data back to your model, and so you're constantly updating and going through this cycle, right? So that you're improving your model with new and more data, and then using that model to generate new variation and characterize it. So it's kind of a feedback loop. And so this characterization component becomes really crucial and a little bit of a bottleneck to some degree, because we can generate as many predictions as we can. Producing the variation is not that big of a bottleneck anymore, but then actually characterizing it across enough locations, right, becomes a challenge. And so for the remainder slides, I'm gonna focus on this area, which is what I'm most passionate about, which is phenotyping. So the way we can characterize data at scale, right, is with precision phenotyping technologies. And really that just means how can we use technology to enhance data that we can collect, not just by reducing accuracy or increasing the accuracy of the data, reducing bias, etc., but also, thinking about what are traits that weren't possible to collect before that could give us some idea of, some insight or additional insights into how different genotypes are responding to their environment. And of course, we want to, essentially remove some of the impediments that we currently get with some of the methods that we use for phenotyping. So again, bias and subjectivity. Most of the traits, and it's still a factor today. Like most of the traits that we collect in the company are on a 1 to 9 scale, which is pretty crazy, right? Like what's a 1 versus a 2? If you have the same person go out and score almost any of these traits, whether it's disease resistance, lodging resistance, etc., the correlation between their own scores in the same day is very low. And this is an example of that. So it's pretty crazy that we still rely on that data for most of the decisions that we make. Of course, there's limitations to human perception and throughput. We get tired. It's really hard nowadays to even get people or students. Previously, we would get these crews of students to go out and collect data. It's really hard to get people that are willing to do that anymore. And so workload is a huge limitation nowadays. And then temporal constraints. Some traits would require you to go out and collect data at a very frequent time intervals. That's not really cost effective. So we don't typically collect any time series traits. And of course, there's a lot of conditions that provide, the concerns regarding safety. So you don't want someone to trip over and hurt themselves, for example, or have to cut, rely on cutting stems or things like that and risk, getting hurt. And so in the end, right, what we care about is increasing the response to selection. So we want to create products that are better. We want to, again, shorten this funnel, widen the funnel, but shorten it by increasing the response to selection. And there's different ways that phenotyping can help with that. you know, if we phenotype better and reduce that error component, we can get better estimates of, genetic variation for the trait of interest. And so we can increase heritability that way. And if we reduce the cost and some of the impediments to some of the traits we collect, and we can phenotype more genotypes in a location, we can increase the selection differential, right? And so all of these elements mean that we would be increasing the response to selection and driving forward products faster, better products faster. In terms of phenotyping, we didn't start that long ago. The first drone that our company purchased was back in 2012. We purchased one drone after some paper came out in Germany where they used drones to do plant counts. Corteva, someone in Corteva purchased the first drone and they were like, okay, let's give it a try. It worked out, it looked promising. So then we started expanding the fleet about 10 years ago. And then we had a couple of drones in the US collecting data. We built the first models. The first model was actually plant counts, and then started expanding to things like plant height. Then by 2016, we started getting drones in other countries because we saw huge promise in that. But then it's like, okay, we're manually processing all of these drone flights. That's really time consuming. So then by 2018 is when we developed the first automated analytics pipeline to process drone data and integrate models, new models for new traits in a more automated fashion. And this also allowed, so before we would store data in these hard drives and just ship them around the country back to the US so that we had, a couple analysts with these gigantic computers processing the data. But then now with automated analytics, we can process everything in the cloud and not need to, be sending data around in hard drives. And some of the traits that we've been working on, they've also drastically evolved. So some of the first traits were things like plant cover and greenness. So you don't really need data science or any fancy models. You're just extracting, okay, how green is my plot clip? Or let me do some basic thresholding to segment things that are green from non-green. And then use that to correlate it to like disease or health or maturity. These are pretty simple traits. They don't necessarily require like machine learning. And so those were some of the first traits that we developed with drones. Then we slowly started, okay, well, let's leverage structure from motion, and then generate these elevation maps so that we can get different elevation features and correlate that with like things like plant height, canopy volume, etc. Right? Lodging is another one. So there's different traits we can get from these elevation maps. And now here we're like, okay, well, maybe we do need some data science resources to start extracting some of these features. But then now, most of the traits that we work with are leveraging machine learning, right? So we're developing models that are detecting objects in the field. Maybe they're classifying objects into scores or into different categories. Maybe we're segmenting different objects of interest, or just making generally a prediction on a quantitative trait. And now, right, we have AI. So this is actually a funny story. So a coworker of mine wanted a diagram showing the evolution of machine learning. So he just put it into the chatbot, give me a visual showing how machine learning has evolved through time. And he got they gave him this image. So now you can just, tell an AI what you want is you're gonna generate it for you. So you can imagine the possibilities there, right? And creating synthetic data sets, helping you. Well, like I was discussing before the G by E modeling with AI, right? Help you see trends in data in very large data sets that you might not be able to with typical machine learning models or typical features that we extract with computer vision, right? So the possibilities are endless. I'll show you a couple examples of different traits that we've collected or that we've developed with some of the more basic machine learning methodologies. And really what I want you to take away is, we have to stop thinking about necessarily like specific replacement traits, but also thinking about what are new traits we can extract that we weren't used to dealing with before. And that's that's a little bit hard in terms of, right? So we can generate these traits, but then how do we actually use them, right? So then there's always that translation that needs to happen in terms of, okay, we can generate this, but then actually working with the end user, in this case, for example, the breeders, to determine, how can these traits be useful is really important, right? Because otherwise you're just generating traits that people are not going to use. And that applies to, so for example, we can generate traits like, I don't know, morphological features that maybe don't mean anything specifically, right? They might be representative of biomass or something like that, but they're just features. And in the end, right, for the most part, traditionally we've relied on correlating them with a specific trait, right, that we collect in the ground. So say biomass or leaf area index. But in the end, right, maybe these features are just a feature that's representative of the morphology that leads to some outcome, in this case, increased yield or yield stability, right? So making that connection and making sure you're maybe providing something that's meaningful, and then working with a breeder doing development so that they understand how they can use the traits that becomes really important. So this is one example for flowering date. It's pretty simple, right? We just, I mean, we fly the field throughout the flowering period. This is a sunflower field. And then we can extract the sunflower heads across time, and then just modeling that through time to get the date at which 50% of plants in the plot reach flowering. It seems pretty straightforward, but this was huge, and has saved us a ton of money, because before they would have to walk the field and collect this data on all of the sunflower fields by hand, and there's hundreds of plants in each plot, so you can imagine how long it takes to collect this data. But also it's probably not very accurate because no one is actually counting the number of sunflower heads in each plot. They're just kind of guesstimating, oh, it looks like 50% of plants in my plot have a flower, right? And so by modeling this, we can get a much more accurate estimate of the flowering date. But more importantly, we can get other insights that we previously would not be able to get. So things like, what's the rate of flowering, right? How fast or does a plot flower? And for example, if you're in a drought environment versus a well-watered environment, do you get different responses in that flowering rate across your different varieties, which could give you an indication into stress resistance or other things. So then it's, again, extracting some of these other traits that maybe before weren't really feasible, aside from just the flowering date, which they would use for things like product placement, right? So then we're getting novel insights from that. And more importantly, again, we reduce the error from the ground measurement, so we can go back and get a trait that's actually a lot more heritable. I'll just skim through this one, but this one is pretty similar. So for wheat lodging, they would go out to the field and just stand at the corner and just say, okay, from 1 to 9, how lodged are you? And then just give it a score. But with drones, we can actually segment the area that's lodged and get more of a quantitative measurement for that lodging trait. And so it's still highly correlated to the 1 to 9 scores, of course, because you're judging the severity of lodging, but you have a more quantitative score. And so we've seen that the heritabilities are much higher. And again, it's going to give you a higher response to selection by utilizing this trait. This is a cool example, and maybe something that most of you have not seen before. But so in cotton yield, so for cotton, if you're trying to get the lint yield, it's really challenging because you have to send these gigantic pickers to the field. They basically harvest all of the cotton balls, and then they have to bring all the cotton balls inside and remove, like, do ginning, etc., remove all of the debris, the seeds, etc., and then they weigh the lint, so the cleaned up lint, and then that's their lint yield. And so they have to do this for all of their research trials. So you can imagine how much work it is to actually get a lint yield estimate for cotton fields. So they don't really plant that many fields because, again, super expensive, not just to transport the picker, but also to get that lint yield estimate. And so we were like, okay, well, before you harvest, you have to defoliate, and we can see these cotton bolls. So can we just use a drone? So we flew a drone. We developed a model to segment out the ball pixels, so the white pixels essentially, and then cluster them into balls, and then get different features. So things like ball cover, the average area of each ball cluster, how compact they are, right? So some of them are more stringy, some of them are more compact. And then train a model to actually predict what that lint yield would be. And at first, the correlations were really promising at a location level, but then when you actually went down to the blob level, so the across location estimates, genotypic estimates, those correlations would completely break down. And what was interesting was that the residual error for those correlations was actually highly heritable. And so what we did was actually develop the concept of using a correction factor at a GE level to correct the raw data level before you conduct before you generate your across location blobs. So what that looks like is, okay, so for each genotype, as long as I have at least that genotype measured in at least one location with both remote sensing and ground data, I can estimate a correction factor, so basically an intercept and a slope for that genotype, and then apply that to all of the other locations that just have remote sensing data. And the reason for that being, there's probably some element to lint yield that we can't visually see. And it could be how dense the ball is. It could be something that's related to the weight of that lint yield that's not visually, when you look at the area of lint, it's not easily translatable, but it's something that's highly heritable, right? So as long as you have that measurement in at least one location for that genotype, you can apply it to all of the other locations. And so when you do apply that correction factor, you get blob accuracies that look like this when you compare the predictions to the ground data, which is really amazing. I mean, that's 0.93, and we've seen that now across almost 6 years of data across all of the locations. So now the cotton team can plant many more locations because they don't actually need to harvest them. They can just use drones to predict what that lint yield will be. And more importantly, because these correction factors are highly heritable, we are trying to leverage genetic relationships to then predict from new material that we haven't actually tested in the field what that correction factor should be, right? Because again, it's something that's highly heritable. So that's another cool example. And I've shown you a couple of RGB drone traits, which again, drones are pretty awesome. They can get data in a field really fast. But there's a lot of other cool technologies that we're trying to leverage. Different sensors, so things like LiDAR are becoming more and more crucial in some of our operations. LiDAR can give us reconstructions of the canopy, right? Especially what collected proximally, so we can get other traits that weren't feasible before, right? Like biomass or number of leaves, maybe features correlated to morphology, like I was talking about. So we can get so much more information now with some of these other sensors. Things like radar can give you insights into like soil moisture and other properties. And then leveraging other types of spectral data as well to get again different traits that weren't feasible necessarily with just traditional RGB. And then more and more we're moving away, not away from drones, but I think we've kind of maxed out what we can do with drones to some degree. We can only get that top view of the canopy, right? And so more and more we're moving towards proximal phenotyping. So it's not just walking the field and collecting data with a sensor, although there is some of that, right? But how do we leverage, say, machinery that's already going through the field to collect data? Let's put sensors in all of our machinery. How do we leverage autonomous platforms, right? There's so many robotics companies nowadays. How can we leverage those to collect data? Even cell phones, right? Everyone has a cell phone. So if you're already walking the field, how can we have you use your cell phone and generate data for us? So we're trying to investigate all of these different options so that we get more and more layers of data so that we can continuously improve some of our decisions. And of course, yeah, autonomy. So we want to rely less on people collecting data and more on autonomous methods for data collection so that we can then leverage the expertise of people to actually analyze data, process data, look at data, and not necessarily, be in the field collecting data. And a cool example of leveraging some of the proximal phenotyping is canola, shatter, and pot drop. And I'll just briefly go over this. I don't think I have too many more slides, but want to make sure we have some time for a discussion. So canola, it was kind of a more recently domesticated crop, and so it still has a lot of like weedy properties. A big one being shatter, it shatters a lot. So basically the pods break in half while still attached to the plant, and so it releases all of the seed. So you get major seed losses due to shatter. And that's one of the biggest problems with the germplasm pool for the canola varieties we have in Corteva currently. And it's one of the biggest, trait targets right now for us. And so before, they would actually place these trays in the bottom of the canopy to collect the seed that was lost. And then they would go out and then collect the trays and then weigh them, like weigh the loose seed. You can imagine this is terrible. You get mice that would just eat the seed, or they would tip over with the wind, or yeah, you get all sorts of issues with these trays. So not a great solution. So then they came up with this method, like, okay, well, in the end, we're trying to characterize seed loss per unit area. So if we take a picture with our cell phone at a fixed distance, and this was one of the breeders that first did this, which is awesome. They're always looking for new solutions to their problems. Well, then I can then count. Okay, this is how many pods or carpels. So the half of the pod that falls is called the carpel that I have in that unit area, and then get a measurement that way. The way we can differentiate intact pods from shattered pods is if they have the pedicel. So, okay, then we can just train a model to find the intact pods or the carpels based on the pedicel, right? And that's what we did, and we actually get really high prediction accuracy. The model does a really good job at differentiate the intact pods from the shattered pods. And we've already deployed the solution, and we've been using it now for 2 years, which is really cool. But of course, it still relies on someone with a cell. They actually put the cell phone on a selfie stick so that they can just take that image close to the ground without needing to bend over. But of course, that's still pretty laborious. So then what we started doing is actually putting this on the combine. So we have RGB cameras right behind the header pointing straight down. And then we can image the ground as you're harvesting, and then quantify, how much shatter you get and how much seed loss you get due to shatter and pod drop while you're harvesting. And so we're leveraging the machinery that's already going through. So there's absolutely no workload involved in collecting this data, but you're getting this really important trait that previously was, there was really no good solution to collect. And so you can get this in all of your yield trials now. This is I just want to make one point here, and I think I've already made this point before, but so canola blackleg is a disease that infects the stems in canola, and right now or the traditional way of phenotyping that is cutting the stem at the base of the plant and then just seeing how much infection there is. It's kind of represented in black, and then they give it a 1 to 9 score, like how diseased are all of the stems in my plot, basically. And if you talk to any pathologists or anyone that collects these disease traits, they'll say that they're experts, right? And they're very hesitant to allow like interns or other people to come in and score them, because it needs to be scored by the experts, people that have been doing this for 10, 15 years. And it's funny because for this experiment, we wanted to develop a better phenotyping solution using imagery, but we needed some ground truth, right? And we know that, of course, they say they're experts, but it doesn't mean that their scores are perfect. So we had 5 experts score the same group of like the exact same samples, side by side. And this is the correlation between the 5 raters, the 5 experts, right? The lowest correlation was around 0.6, the highest one around 0.8, right? So even these experts don't necessarily agree with each other, which is, how most of these traits go. So there's a lot of error and bias in how these scores are made. Um, and so what we did was just develop a cell phone solution. Okay, then, we can have any interns go out and just cut the stems and then take an image. We tried developing an actual machine that was gonna do the cutting, etc., but it ended up not being a lot slower, and not as feasible as just cutting the plants by hand and then just taking a cell phone image, and then just training a model to find the stems and then predict the score. And in the end, what we get is a machine learning model that's unbiased, right? Because it's always going to generate the same score. And it's highly correlated to the ground truth, which in this case we said is the median score across the 5 raters. And more importantly, we no longer need these experts that are scientists, right? So they get paid a lot more to go out, and do these assessments. We can send an intern or a student or the high school crew, etc., to collect these images. And you have a record of these images. So if something doesn't line up, you can always go back and actually view, hey, what happened to this check? It was supposed to be resistant, but it's showing a lot of disease. Is that real? Right? You can go back and actually see these images and figure out what went wrong. And so you have a kind of a long-term record of those of the phenotypes. So, I've showed you some examples. I wanted to talk about, things that I consider are exciting challenges, and especially from the modeling side. One of the biggest challenges we face is sensor or platform turnover. So let's say we develop a model with a specific sensor that's going to be in the specific drone, right? It's the Sony camera, it's the new, high-end camera. They're expensive, but they have a lifespan, right? And probably 3 to 5 years from now, they're not going to even be manufacturing that camera anymore, right? And so one of the biggest challenges we face is that when you train a model on a specific data set, models don't tend to generalize well into new data sets. And so suddenly when they discontinue this camera, and our old platforms start to die off, right? They have a life cycle and we need to buy new ones, and we find a new replacement sensor. It looks very similar, etc. But then suddenly none of our models work, and we have to collect new data and retrain all of our models with the new sensor. That's happened many times before for different, machine learning types of models where we're detecting objects, or segmenting different objects, etc., from imagery. So then the question is, how do we start to build models that are agnostic to sensor or platform? For example, and by platform, I mean, I don't know, moving from drone to proximal or between different proximal platforms, maybe a robot versus someone that's, pushing a sensor through the field, right? Or even simple things like, for example, in Latin America, we have a different row width spacing in cornfields than we do in North America. So they plant 50-centimeter row spacings because that's what their equipment can handle, versus North America plants, 76-centimeter spacings. So even there, like we've seen that models for different traits collected proximally don't translate, because suddenly these objects are a lot closer in Latin America. So how do we start making models that generalize better across different conditions, different sensors, different platforms? So that's a big area of interest. We had an open innovations initiative in Corteva where we looked for proposals externally for to come up with different solutions that we can try. And so we picked the top proposals and are currently working on testing some of those out to see how we can improve model generalization. Another another big area is, of course, data storage and computational costs, right? How collecting data in the field is not actually that expensive. Like it is to some degree, but we can get labor that's fairly cost efficient. And so if you're spending more money on running a model and generating data from imagery than you would be just sending someone out to collect the data by hand, then you're losing, right? Unless there's other benefits, right? Like increased heritability, etc. But in the end, the bottom line, right? You can't spend too much more money running models and storing data than you would just collecting the data by hand, right? So that's still an issue. We're getting better at reducing computational costs, doing model optimization, leveraging cloud resources, and so the archiving data, tiering data, et cetera. And so this has become better, but it's still always a concern and a challenge. And then most of the traits we collect are at a plot level in research. So even thinking about getting down to plant level or even sub-plant level data, how do we feasibly collect this? How do we build models to do some of this? That's still an area that that proves to be challenging for us. And so, yeah, some final conclusions, right? We can leverage novel genetic variation to produce better varieties and hybrids, but often introducing variation has confounding effects and reacts differently compared to native variation, and you get effects like penetrance, playtropy, etc. And then also, of course, you get G by E patterns, and so there's different ways to start to model G by E patterns, and I showed you two of them. There's a lot of environmental data and different ways to model the environment that we can leverage, especially leveraging things like satellite imagery. And of course, advancing phenotyping allows for better characterization of introduced genetic variation, which in the end will be key to accelerating response to selection. And lastly, with AI and some of the new technologies, we're going to start to get a lot more insights than we previously were before. And so then the challenge becomes how do we make sense of that insight, and how do we start to integrate it into some of the traditional frameworks within breeding, right? And yeah, that's the end of my talk. So I don't know if anyone has any questions.
Hi, I have a question.
Yeah.
So, first, thank you for your presentation. It's a very good presentation. I have a question is that you mentioned that you use like the AI or deep learning in this like these technologies. And we also know that nowadays in like the transformer architectures, they are willing perform I mean, they are really use like a ChatGPT or cloud or something like that.
Yeah.
So, I mean, do you try these things in using these models to prediction in this our agriculture field?
Yeah, definitely. So transformer models, we have started using or started testing them and using them as a solution to get around that kind of, developing more sensor agnostic or even time insensitive models. We've seen definitely improvements in leveraging some of the transformer models that can generalize a little bit better. And so that, yeah, so definitely starting to leverage more of those types of architectures to improve the models that we're developing. Things like like ChatGPT, etc. We're starting to investigate different uses. So, for example, like how can we use them to help farmers decide what lines or what varieties they should plant in their field based on their geography and weather data, etc. So they can interact right with kind of as a chat and help them come up with some plan for management, etc. There's other ways to use it, right? Like synthesizing databases. So we have so much like a huge database with protocols and different information on how to even we have so many different softwares and things like that. So then you can basically we have an internal version where you can ask it, hey, how do I don't know, use X software, and it gives you all of the protocols and instructions on how to install and how to use it, etc. So just synthesizing knowledge base, or even things around safety, right? Like safety trainings. So synthesizing information around safety trainings for a specific purpose to generate different SOPs, etc. So we're definitely using it in many different contexts. Those are probably the ones that I can mention. But yeah.
So how many source or how many times do you need to training these models? Because I know that the traditional models like a G-block or RF,
Yeah.
these things we can do like even in our own computer or laptop. But I know that for like a deep learning or machine learning, they need a lot of sources and
Yeah.
they also need a lot of time. So I just wondering, how many times like you need when you're training a new models?
Yeah, that's a great question. So normally what we do is we have this, we call it the stages and gateways process. So we always start pretty small, but keep in mind, right, that for most of our research trials, we're actually we have a pretty big testing footprint. And now we have drones and a lot of our proximal hardware in all stations globally. And so asking people to go out and collect data is not really a big limitation anymore. And now we have satellites, so we can just task it, right? Like say, I want to collect X, all of these time points across all of these geographies. So for us, the limitation is no longer getting the data, like maybe it is more so in like some academic environments, right? Where you have to like plan a specific experiment and buy the technology to collect data, etc. But normally we start pretty small. A lot of times within 2 years, we can roll out a new trade and deploy it. We start small, we test a lot of different technologies, different protocols, different models, figure out what works best, and then go towards wide area testing as a second stage. And there we just pick, okay, this is the one protocol, one technology, and we're gonna collect it across all of these different regions that say grow the crop of interest. Um, and so normally within 2 to 3 years, we can get enough data to train a pretty robust model. We'll consistently monitor it to make sure that, so for example, the first time we developed the plant counting, corn counting model, the model had never seen soils from Brazil, and the soils in Brazil are really red. And so it had a hard time kind of generalizing into Brazil soils. And so then it's like, okay, it's failing, so let's just, integrate some red soils into the training data. But after that, normally we have enough data embedded that unless you have something very, very, very drastic, like we completely switched over the sensor on the drones, and we start to see some failures, then that's where we start to get into trouble. But then with some of the data augmentation techniques, making sure we have a mix of platforms from small drone platforms to large drone platforms. So making sure we're actually integrating data from the different platforms in our training data allows us to develop models that are, not going to need to be retrained every time we switch over. So again, it's kind of really trait dependent, but we haven't seen that there's a huge drift in the data that we're acquiring. And so often unless we go to a region that's completely different, often our models just work well for multiple years. Sometimes we do decide to switch them over and maybe train a new architecture, maybe because we are trying to increase the accuracy and model architectures are constantly evolving. So we call it like a continuous improvement project. And so, sometimes we'll take on those types of projects, but they're not necessarily because the model is failing. We just think we can develop a better model or more robust model.
Thank you. So, last small question. So, you mentioned that you also use the saturated data,
Yeah,
right? So, is that expensive? I mean, comparing to the
yeah.
Zoom anything?
So it currently is expensive. We're expecting the cost to come down. I believe right now, so for the 30 centimeter data sets, each acquisition, and keep in mind, one acquisition can actually cover a huge area. So if you plan it appropriately, you could actually get many different trials or field locations in one image, right? Because it's I don't know the size. I can't remember off the top of my head, but we can get many fields in one image because it's a huge area. And so each acquisition is, I think it was close to $200. Which, if let's say, I don't know, you're imaging 10 locations in one image, then really the cost isn't that much, right? If you think about the cost of driving to the place and then spending all day collecting a specific trait. But we are expecting these costs to start to come down over time because a lot of these technologies are very new.
Okay, thank you.
I have a question. If You have
Yeah,
time?
yeah.
So
I can
I
stay for another
remember
minute.
you mentioned the DEM model for measuring plant height and lodging. So
Yeah,
I'm just curious that if we're using RGB imaging for the plant height and lodging, could you tell me the resolution of your RGB camera that works well for your modeling? And
yeah.
also another question is that when it comes to measuring the plant lodging, do you directly measure it itself, or you compare it with the plant heights that are upright and then say, okay, this is upright, and then that one is like 20% less than the upright one, so it's large like this much.
Yeah, that's very dependent on the crop. So for the example that I showed you in wheat, they have a specific protocol. So if it's leaning more than, I think it's, I forget the angle, I think it's 30% or something, then they'll score it based on what percentage of my plot is leaning above or below that angle, right? And so in the end, they'll give it a 1 to 9 score, and that's what we're actually using as the comparator. But in the end, what we're training our model in the RGB case, and I can share maybe a follow-up via email, the link, because we actually just published the method for that project. But what we're doing is actually visually segmenting out the areas that are lodged, right?
Mm-hmm.
Based on the pattern. And so it's just kind of more texture based. For other crops, we do rely more on the DEM than the RGB image. Other crops, we actually use LiDAR instead of RGB. So crops like corn, we get better estimates of lodging with things like LiDAR. So it's very crop dependent and how they score it on the ground.
Oh, thank you.
Um,
And can you tell me the RGB resolution of your camera? Do you remember it?
Oh, the GSD, the resolution varies because we have very different platforms, but the GSD is about 1.5 centimeters right now.
Oh, okay.
Yeah.
Okay. So is it okay if I send you an email after this for the follow-up?
Yeah, no problem.
Thank
Yeah,
you. Thank
absolutely.
you so much.
Okay, I have to go to another meeting, but great to meet you guys. And thank you.
Thank
Bye.
you.
Thank you so much.